Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be here for another deep dive.
Yeah, so imagine a continent of solid 2-inch thick steel. Just a massive, perfectly uniform, expansive metal, stretching for miles.
Right, just infinite flat steel.
Exactly. Now imagine taking a microscopic, like a needle-sized drill bit, and poking a single invisible pinhole dead in the center of that continent.
Just a tiny void.
Yeah. If you put that steel continent under tension, the physical stress at the exact edge of that microscopic, barely there hole doesn't just, increase slightly.
Doesn't just bump up a bit.
No, it immediately violently triples. A tiny speck of nothingness literally multiplies the forces tearing at the steel by a factor of 3.
It's wild to think about.
It is. Like, why? So today, we are tearing down the engineering physics of empty space. We are diving into the mathematics of holes, stress concentration factors, and, well, the invisible battle happening inside every piece of metal you've ever drilled into.
It really is, it's one of the most profound paradoxes in mechanical design, honestly. Yeah, because you take a perfectly good load-bearing material, right, and you intentionally remove a piece of it. You create a void.
Which feels like you're just making it weaker.
Exactly, but that absence of material, it completely redefines the structural reality of the entire part. It's not just about the metal you took away. It's about the geometric shock wave that the void sends through the material that remains.
Right, because structural members with transverse holes are just everywhere. Like, if you were a mechanical engineer, you just can't escape them.
You really can't.
You're designing crankshafts with oil galleries, leaf springs with clamping bolts, ridge gussets packed with rivets, aerospace skin panels riddled with fastener hole.
They are ubiquitous in engineering.
So our mission for this deep dive is to extract the absolute truth of how these empty spaces disrupt stress.
Because there's a lot of confusion out there.
So much. We are getting answer the questions that constantly plague engineering forums, translate the intimidating charts into physical intuition, and give you the factual reality of how to design structures that actually survive the real world.
And to build that intuition, we really have to reframe what a hole actually is.
Yeah, how so?
Well, the fundamental trap I see so many young designers fall into is viewing a hole merely as a loss of cross-sectional area.
Like just doing basic math on the surface area.
Right. They think, I removed 10% of the metal, so my part is 10% weaker.
And that's not true.
That is a highly dangerous underestimation. A hole is a geometric obstacle. It forces the internal forces, the load paths running through the solid, to violently detour.
Okay, so if I'm visualizing this, I always think of it like a crystal lattice.
That's a good starting point.
If I'm pulling on a plate of steel, every iron atom is holding hands with its neighbors, sharing that microscopic load evenly across the entire width, right?
Exactly, a nice even distribution.
But the moment I drill a hole, the atoms right at the boundary suddenly have no neighbors on one side.
They're just grasping at air.
Yeah, they reach out, grab nothing, and so the entire physical burden they were supposed to carry gets dumped instantly onto the atoms directly adjacent to them, right on the edge.
That is a phenomenal way to conceptualize it, actually. You're describing the disruption of the load path at the atomic scale.
It makes it feel more real.
It does, because the stress isn't some abstract, magical aura. It's literally the interatomic bonds stretching under excessive burden.
Right.
At the macro scale, the classic analogy is a wide, rapidly flowing stream of water.
Okay, a stream.
If you drop a perfectly round, smooth boulder right into the middle of that stream, the water doesn't just casually absorb the obstacle.
No, it has to rush around it.
Exactly. The water directly in front of the boulder slows down to a halt, but the water squeezing past the left and right sides of the boulder, it speeds up immensely. It bunches together.
And that bunching is the stress.
Yes. That violent bunching of flow lines is exactly what we measure as the stress concentration factor. We are calculating the ratio of that peak, localized, bunched-up stress to the baseline calm water stress of the surrounding material.
Okay, let's unpack this. Because before we get deep into the weeds of how different shapes change that bunching, we really need to lay down our terminology for the class.
Definitely necessary.
Because if you open any engineering textbook or design manual, you are going to be hit with specific notation, specifically the battle between KTG and KTN.
Ah, yes, the two factors.
So KT obviously stands for the theoretical stress concentration factor. But that G and that N, they change everything, right?
They alter the entire mathematical foundation of your safety analysis. So the G stands for gross.
Gross area.
Right. KTG is the gross stress concentration factor. This is the ratio you get when you compare the violent peak stress right at the edge of the hole to the overall uncut gross area of the part.
Meaning you're looking at the whole part.
You are basically analyzing the stress multiplier as if the hole wasn't even there stealing your cross-section.
Which, I mean, that feels a bit like cheating the math.
It is a bit of a theoretical fantasy, yes.
It's comparing the worst-case scenario to a fantasy world where you didn't even drill the hole. So the alternative is KTN, the net factor.
Exactly.
I assume this means we are comparing the peak stress only to the remaining solid material, like the actual minimum net cross-section that is physically left over to carry the load.
You've got the distinction perfectly. The net factor accepts reality.
It deals with what's actually there.
Right. It compares the peak stress to the nominal stress flowing through the narrowed bottleneck of material beside the hole.
Makes total sense.
And it might seem like, semantic bookkeeping right now, but later on, when we discuss materials undergoing cyclic fatigue, choosing the wrong factor between gross and net won't just fail your exam, it will cause your design to physically fracture in the field.
Yikes. We will definitely circle back to that nightmare scenario.
Yeah.
But let's start at the absolute beginning, the baseline.
The classic starting point.
The scenario every mechanical engineering student stares at on a whiteboard during their junior year. We have a single, perfectly circular hole in an infinitely wide, infinitesimally thin, flat panel.
The holy grail of theoretical stress analysis.
And we are pulling that panel in exactly one direction, pure uniaxial tension.
Right. To translate the math of this scenario into something physical, we have to look at the elastic stress distribution formulas derived in polar coordinates.
Sounds intimidating.
It can be. Now, I won't torture everyone with the full differential equations, but the physical takeaway is absolute.
Okay, what is it?
When you pull this infinite plate, the stress distribution is not uniform around the circle. The stress reaches its absolute mathematical maximum at the exact edges of the hole that sit perpendicular to the direction of your pull.
Let me lock that in.
Yeah.
If I am gripping the top and bottom of this steel plate and pulling it straight north and south,
yes,
the maximum stress isn't at the top and bottom of the hole, it's at the east and west edges, the sides of the hole.
that is correct. Think back to the boulder in the stream.
Right, the water flowing.
The water isn't moving fastest at the front or back of the rock. It's whipping around the extreme left and right flanks.
Oh, it's a great visual.
And the mathematics dictate a very specific, undeniable ratio for those flanks. The formula proved that the maximum stress at those east and west points equals exactly 3 times the nominal applied stress.
3 times.
Yes. Therefore, your baseline theoretical stress concentration factor, your KT, equals a perfectly clean 3.
Now, here is where my internal skeptic flares up.
Yeah.
And it's the exact same pushback I see engineers posting on forums all the time.
I think I know what you're going to ask.
Let's take the theory out of the textbook and put it into my continent of steel. If I have a massive, infinitely wide plate of solid metal and I pull it,
Okay.
and the stress is, say, 10,000 psi everywhere, if I take a microscopic drill bit, a fraction of a millimeter wide, and I plunge it into the dead center of that steel continent.
A tiny, tiny pinhole.
Yeah, does that tiny, almost invisible speck of missing metal really triple the stress at its edge to 30,000 psi?
Yes, it absolutely does.
Seriously.
And that is the exact conceptual hurdle that trips up incredibly smart people. The multiplier, that factor of 3, is dictated entirely by the geometry of the obstacle, not by its absolute physical size.
The size doesn't matter at all for the multiplier.
A microscopic pinhole behaves exactly the same way as a circular hole the size of a football stadium, provided the surrounding panel is infinitely wide relative to the hole.
It is hard to wrap my head around.
Think of it this way. The water rushing around a tiny grain of sand experiences the same proportional geometric bunching as water rushing around a massive boulder relative to the scale of the object.
It just feels wrong. It feels like a tiny pinhole shouldn't have the leverage to triple the stress of a massive plate.
It feels wrong because our brains naturally conflate the intensity of the stress with the volume of material affected by it.
Okay.
And that brings us to the saving grace of mechanical engineering stress decay. Yes, the stress right at the boundary of that microscopic pinhole triples to 30,000 psi.
Right.
But we have to analyze how far that triple stress actually penetrates into the surrounding steel continent. The data proves that this multiplier is intensely localized.
Meaning the damage is contained.
Yeah.
Atoms a few inches away have no idea the hole even exists.
Exactly the right framing. Let's look at the mathematical decay of that circumferential stress as you move away from the hole along that east-west axis.
Okay.
If your hole has a radius of a, then by the time you travel a distance of just 5 times them from the center.
So 5 radii out.
Yes. By that point, the circumferential stress has plummeted. It has decayed down to 1.02 times the nominal stress.
Oh, wow. Ah, so the drop-off is practically a cliff.
It is very steep.
If I have a 1-inch radius hole, by the time I am 5 inches away from the center, the stress multiplier is basically gone. It's just 2% higher than normal.
Exactly. And if you have a microscopic pinhole with a radius of 1/1000th of an inch, the stress is back to normal just 5/1000ths of an inch away.
That's tiny.
The boulder only causes violent rapids immediately adjacent to its surface. A few feet down the bank, the water is flowing smoothly and evenly again.
That's a huge relief.
This violently localized nature of stress concentration is the only reason human civilization can build things. It's why you can drill a hole in a steel beam to hang a light fixture without the entire skyscraper instantly shearing in half.
Because the damage doesn't reach the edges of the beam.
Exactly. The elevated stress is real, but it is confined to a tiny microscopic halo around the cut.
That makes so much more sense. The peak is high, but the mountain is incredibly narrow.
Precisely.
But, let's leave the realm of theoretical continents of steel. In reality, my steel plates have finite widths.
Yes, the real world.
I'm usually designing like a narrow metal strap, like a tension bracket, where I have to drill a 1-inch bolt hole right through the middle of a 2-inch wide piece of flat bar.
So the hole is half the width.
Yeah, the hole is taking up half the real estate. I can't imagine a KT of 3 applies there, because the stress doesn't even have 5 radii of room to decay before it hits the outside air.
It doesn't apply. And this is where the math transitions from elegant, clean polar coordinates into the gritty reality of empirical testing.
Real-world data.
Yes. When your hole starts consuming a significant fraction of your panel width, the outer boundaries of the panel start fighting back.
Fighting back.
The stress flow lines are being squeezed between the edge of the hole and the edge of the part. They can't flare out naturally into an infinite plane.
Oh, they are trapped in a bottleneck. So if the factor isn't 3, how on earth do we calculate it?
This is where we rely on the foundational work of researchers like R.C.J. Howland, and later, the brilliant empirical formulas developed by R.B. Haywood.
Haywood.
Yes, Haywood ran the numbers and the tests to cover this finite width reality. He developed an equation that states the net stress concentration factor, KTN, equals 2 plus the cube of the quantity 1 minus the ratio of your hole diameter to your panel width.
Okay, audio math is always tough. Let's translate that into a physical tug of war.
Sure.
We have our hole diameter, let's call it D,
Yeah.
and we have our total panel width, H. Haywood is basically saying we need to look at the ratio of D over H.
Yes, that ratio is the key.
If I have a tiny hole in a wide plate, D over H is practically 0.
Correct. And if you run the math, 1 minus 0 is 1. The cube of 1 is 1. And 2 plus 1 brings us right back to our theoretical baseline of 3.
Oh, wow. So the formula holds up perfectly for wide plates. It matches the infinite plate theory.
It provides a perfect bridge to the infinite theory.
But let's push it to the extreme. What if my hole diameter D is getting massive? Like it's chewing up the whole bracket. The diameter's approaching the total width H.
So mostly hole, very little metal.
Yeah. That ratio of D over H approaches 1.
Let's follow the physics. If the ratio is 1, then 1 minus 1 is 0. The cubed term completely vanishes.
Which means the KTN approaches 2. Wait, it goes down.
It does.
As the hole gets bigger and eats more material, the stress multiplier drops from 3 down to 2.
It does, based strictly on the net area. The geometric multiplier softens because the material is acting less like a plate with a hole and more like 2 parallel strips of metal.
Oh, I see.
But this mathematical quirk reveals a truly fascinating physical phenomenon, one that was observed in deep detail by researchers like A.M. Wall and R.B. Wooks.
What do they see happening to the metal?
Imagine your hole diameter is 99% the width of your panel. What you have left on the left and right sides is not a flat plate anymore.
No, obviously.
It is just 2 microscopic, hair-thin filaments of metal trying to hold the entire load.
Just tiny little slivers of steel spanning the gap.
Yes. And Wall and Bukies observed that under load, particularly when dealing with finite deformations in plastic models, something incredible happens.
What happens?
Those infinitely thin filaments don't just sit there and take the eccentric stress. Because they are so thin, they physically warp. They bend inward toward the center of the empty hole as the part stretches longitudinally.
Wait, they acting like strings being pulled taut. When you pull a loose string, it straightens out to perfectly align with the force.
That is the exact mechanism. Because those slivers physically move and realign their geometry with the primary load vector, they eliminate the eccentric bending forces.
Oh, wow.
They allow the stress to distribute almost perfectly uniformly across their tiny microscopic cross-sections.
Meaning the stress concentration multiplier drops even lower.
Theoretically, yes. For large plastic deformations where the material can flow and realign, the KTN can theoretically plummet all the way down to a perfect 1.0.
1.0.
The multiplier vanishes entirely because the geometry has essentially deformed into two straight wires pulling in perfect tension.
That is a wild survival mechanism built into the physics of the material.
It is, but I must add a massive blinking caution light for any engineer listening.
A warning label.
A huge one. This drop to 1.0 only happens in large plastic deformations, meaning the part is already permanently yielding and stretching out of shape.
It's already failing, basically.
Yes. For tiny, rigid, elastic deformations, the safe zone where we actually design parts to live the inward movement isn't significant enough to relieve the bunching. In the elastic zone, the KTN bottoms out and stays stubbornly at 2.
Got it.
Furthermore, as researchers Belli and Apple correctly point out, if you have a hole that consumes 99% of your part's width, the microscopic drop in your theoretical stress factor is entirely irrelevant.
Because your part is going to snap anyway. If you leave a hair-thin sliver of metal to hold up a tractor, it doesn't matter if the multiplier is 2 or 1. The baseline stress is in the millions.
Precisely the point. The net area is so catastrophically small that failure is guaranteed regardless of the multiplier, but it serves as a beautiful demonstration of how geometry and force constantly negotiate with each other.
I love that. The material is actively trying to find the most efficient load path.
It really is.
But, that localized stress decay is fascinating for a flat plate in a tensile testing machine. In the real world, my designs aren't just being pulled in one direction.
Very rarely are they.
If I'm designing the pressure hull of a deep-sea submersible, the ocean isn't just pulling it end to end, it's crushing it from all sides simultaneously.
True 3D loading.
How does this boulder in a stream analogy hold up when the stream is hitting you from every possible direction?
It completely overwrites the stress map. When we introduce biaxial stress loading the material in 2 perpendicular directions, simultaneously we enter a much more complex arena.
I can imagine.
To navigate it, engineers rely on the principle of superposition. Because we are operating in the linear elastic range of the metal, meaning it springs back to its original shape when you let go, we don't have to invent entirely new exotic math.
So if I'm guessing how superposition works, if I know the stress field for a horizontal pull, and I know the stress field for a vertical pull, I could literally just lay those 2 mathematical maps on top of each other and add the numbers together.
You've hit the nail on the head. Superposition is the mathematical equivalent of stacking transparent maps.
Nice.
Let's build the model. We pull horizontally on the plate with a primary stress we will call sigma 1. We pull vertically with the secondary stress we will call sigma 2.
Okay.
To make our equations universal for any load, we define a simple ratio. Lambda. Lambda is simply sigma 2 divided by sigma 1.
So lambda is just our gauge for how hard the vertical pull is fighting against the horizontal pull. If the vertical pull is half as strong, lambda is 0.5.
Exactly. Now, using that stacked map of superposition, we can predict the peak stress at any point on the hole's edge.
Okay, let's hear the formula.
At the top and bottom edges of the circle, the peak stress is equal to sigma 1 multiplied by the quantity 3 times lambda minus 1. Conversely, the peak stress at the left and right edges of the circle equals sigma 1 multiplied by the quantity 3 minus lambda.
Okay, I want to plug some real visceral numbers into this because I know this leads to an absolute aha moment for anyone designing pressure vessels.
It really does.
Let's look at equal biaxial tension. I am inflating a perfect metallic sphere like a high-pressure gas storage tank. The internal pressure is pushing out equally in every single direction.
A classic spherical pressure vessel.
That means the horizontal stress, sigma 1, is exactly equal to the vertical stress, sigma 2.
They are identical, which means our ratio, lambda, equals exactly 1.
So let's run your formula for the left and right edges. It was sigma 1 times the quantity 3 minus lambda.
Yes.
3 minus 1 is 2. which means the maximum stress concentration factor drops from a 3 down to a 2.
The math holds. And if you check the top and bottom edges using the other formula, 3 times lambda minus 1.
Okay, 3 times 1 minus 1.
That also equals 2.
The stress factor is 2 everywhere.
It is perfectly uniform all the way around the entire circumference of the hole.
Wow.
Because you are pulling equally in all directions, the geometric bunching effects are essentially interfering with each other. The horizontal pole wants to bunch the stress at the top and bottom, while the vertical pole wants to bunch the stress at the left and right.
And they just cancel out.
They fight each other to a draw, and the overall stress state settles into a highly stable, uniform KT of 2.
That is incredibly elegant. But what if the forces aren't playing nice?
They often don't.
What if I'm not inflating a sphere, but twisting a panel?
Hmm.
What if I'm stretching the metal left to right, but simultaneously squishing it, compressing it, top to bottom?
That is the notorious state of pure shear, and it is violent. In this scenario, your vertical stress, sigma 2, is the exact negative of your horizontal stress, sigma 1. One is pulling, the other is pushing with the exact same force.
Okay.
Therefore, our ratio, lambda, equals -1.
Oh boy. Let me run the mental math on that. For the left and right edges, 3 minus lambda, that becomes 3 minus -1.
Correct.
Which is 3 plus 1, 4. The KT jumps to 4.
It jumps to 4, and it creates an incredibly volatile situation. The tension and compression fields are no longer fighting each other to a draw. They are constructively interfering.
Making it worse.
Much worse. The geometric squeezing of the compression adds to the geometric stretching of the tension, conspiring to rip the hole apart at the seams.
Which is a brilliant proof of why you can't just be lazy as an engineer, slap a standard 3 times safety factor on every hole in your CAD model, and call it a day.
You really can't.
You have to trace the load path. You have to know how the part is being loaded, not just that it's being loaded.
Exactly right.
But let's add another layer of reality. We talked about spheres and flat plates. What about cylinders?
Cylindrical shells.
Most of the pressurized things we build, rocket bodies, submarine hulls, oil pipelines, are cylinders. Wrapping a flat plate into a tube has to mess with the physics.
It introduces an entirely new, highly destructive variable, curvature.
Curvature.
A flat plate, even a biaxially loaded one, is a highly idealized scenario because all the forces act entirely within the flat plane of the material. But the moment you wrap that plate into a cylinder and pressurize it, the physics change.
Because it's trying to unroll.
You still have membrane stresses stretching the metal, but now you introduce immense bending stresses right at the edge of the hole.
Because the hole is essentially a weak spot that breaks the structural continuity of the arch. It wants to bulge out radially away from the center of the pipe.
That is the exact physical mechanism. The solid metal around the hole has hoop strength to resist the internal pressure, but the empty void does not.
So it pushes out.
So the internal pressure pushes the flexible edges of the hole outward, creating a local bulge. To calculate the severity of this bulging stress, aerospace and pressure vessel engineers rely on a critical, dimensionless parameter called epsilon, derived from shallow, thin shell theory.
Okay, hit me with epsilon. How do we weigh this bulge?
Think of epsilon not as a string of random numbers, but as a mathematical scale balancing two different geometric realities.
Okay.
Epsilon equals a constant 0.639 multiplied by the ratio of your hole radius to the mean radius of your cylindrical shell.
Hole radius over shell radius.
Then you multiply all of that by the square root of a second ratio, the thickness of your shell divided by its mean radius.
So it's heavily dependent on how thick the wall of the pipe is compared to how big the pipe is overall. Why is this specific messy parameter the gold standard for an engineer designing a rocket?
Because epsilon serves as the ultimate boundary guard. It dictates the region of validity for all your assumptions. Let's look at aerospace. If you are designing a rocket body or a commercial airplane fuselage, you are dealing with incredibly thin aluminum or composite shells over massive diameters. The shell thickness is tiny compared to the overall radius.
It's like a soda can.
Exactly. In a soda can scenario, this geometry drives your epsilon value to relatively large numbers, say 2, 3, or 4.
And what does a large epsilon mean?
When epsilon is that high, the theoretical KT factors in the engineering charts absolutely skyrocket. They detach from the flat plate baseline entirely.
Oh, wow.
Because the shell is so thin, it offers almost no bending stiffness. The bulging effect at the hole is severe. You aren't dealing with a gentle flat plate KT of 2 or 3 anymore.
What are we dealing with?
The bending stress might drive your local multiplier to a factor of 5, 6, or even higher.
That's terrifying. But what if I'm on the other end of the spectrum? What if I'm not designing a thin aerospace soda can, but a massive, thick-walled hydraulic pipe for an excavator?
In that heavy machinery regime, your wall thickness is very large relative to your cylinder radius. If you plug those chunky numbers into the formula, epsilon plummets to a very small decimal, like 0.5 or less.
And when epsilon is tiny?
The curvature effectively ceases to matter.
Really?
The thick walls possess so much inherent bending stiffness that the hole cannot physically bulge outward. The structural integrity holds the curve, and the thick pipe behaves almost identically to the theoretical flat plate we started with.
It's fascinating.
Epsilon is a beautiful metric because it mathematically guides your physical intuition, telling you exactly when curvature is a deadly threat and when it's negligible.
Here's where it gets really interesting. Speaking of physical intuition, let's follow the logic trail to a completely different shape.
Different from a circle.
Yeah, because my
Uh-huh.
intuition says if a circular hole causes a baseline 3 times stress multiplier, and even in the best case biaxial load, it still causes a 2 times multiplier. Why on earth are we so obsessed with drilling circles?
It's a great question.
If circles are such terrible structural bottlenecks, why do we use them everywhere? Which brings us to perhaps the most famous engineering trivia question of all time. Why are airplane windows oval instead of round or square?
It is the ultimate story of engineering optimization forged in tragedy, and it all revolves around the mathematical properties of the ellipse.
The ellipse.
The theoretical baseline for the elastic stress distribution around an elliptical hole in an infinite plate was cracked by the British engineer Charles Inglis back in 1913.
The Inglis formula. I know this is foundational. How did he map the stress for a stretched-out circle?
Inglis realized that an ellipse gives us 2 levers to pull rather than just the single radius of a circle.
Okay, 2 levers.
Let's assume we have an elliptical hole with a horizontal semi-major axis we'll call A and a vertical semi-minor axis we'll call B. So it's an oval sitting flat on its long side.
Got the picture.
If we take our plate and pull it with a uniaxial tension straight up and down, pulling it perpendicular to that long A width, Inglis proved that the gross stress concentration factor, KTG, equals 1 plus 2 times the ratio of A over B.
Okay, 1 plus 2 times A divided by B.
Yes. Alternatively, you can express it in a way that feels more intuitive for machinists and designers, using the actual sharpness of the curve at the edge.
How does that look?
It's mathematically equivalent to, say, KTG equals 1 plus 2 times the square root of A divided by R, where R is the radius of curvature at the sharpest extreme of the ellipse.
I want to stress test this formula. Let's put it through some extreme boundary conditions to see if the physics hold up.
Let's do it.
Let's start by morphing our ellipse back into a perfect circle. In a perfect circle, the width A and the height B are exactly identical.
They are. So the ratio of A divided by B is simply 1. The formula becomes 1 plus 2 times 1.
Which is 3. We arrive right back at the baseline multiplier for a circular hole. Inglis's math is perfectly backward compatible.
It is. Now let's take it to the other, terrifying extreme.
Terrifying.
Let's squeeze the ellipse. Let's make the height incredibly tiny, approaching 0, while the width, A, remains large. Visually, you have an infinitely narrow, horizontal slit in the metal.
If I'm visualizing that, it's no longer a hole. You just described a razor-sharp crack propagating through the steel.
I did. And look at what the math does. When B approaches 0, the ratio of A divided by B involves dividing a whole number by a near-zero decimal.
Which goes to infinity.
The resulting fraction explodes, the stress multiplier skyrockets exponentially toward infinity.
The sharper the crack, the more the stress multiplies, tearing it even further open.
Exactly. This is the entire foundation of linear elastic fracture mechanics. A sharp crack creates a near infinite stress concentration at its microscopic tip.
That's why cracks are so deadly.
The interatomic bonds at that tip are experiencing forces hundreds of times higher than the surrounding metal, which is why, once a crack initiates, it takes very little additional force to unzip the metal completely.
Which is exactly what happened to the de Havilland Comet. We have to talk about that history, because it proves why we care about these shapes.
A very dark day for aviation.
The Comet was the world's first commercial jetliner in the 1950s. It was a marvel. But then, they started falling out of the sky, exploding midair.
It remains one of the most sobering lessons in modern engineering. The Comet was designed with square passenger windows.
The square windows.
Now, they weren't perfectly sharp squares. They had slightly rounded corners. But as we just discussed, a tight radius of curvature acts identically to a tight ellipse.
That sharp R value in the formula.
The engineers at the time didn't fully appreciate the magnitude of the stress bunching at those square corners under cyclic pressurization.
Every time it took off.
The airplane would take off, the cabin would inflate like a balloon, the corners of the square windows would experience massive stress concentrations, and over hundreds of flights, microscopic fatigue cracks initiated at those corners. Eventually, the fuselage violently unzipped at altitude.
So how did the industry fix it? Walk us through the optimization of the modern airplane fuselage using Inglis's insights. Why vertical ovals?
To solve the window problem, we have to treat the airplane fuselage for what it truly is. A massive flying pressure vessel.
Okay, a pressure vessel.
It is a sealed cylinder maintaining a survivable atmosphere while cruising through a low-pressure void. The internal cabin pressure is desperately trying to tear the aluminum skin apart in two distinct directions simultaneously.
Biaxial stress again.
First, you have the hoop stress. This is the tangential force pushing radially outward, trying to split the cylinder open down the middle.
Like a hot dog bursting its casing on a grill.
A vivid, if messy, physical analogy. Second, you have the axial stress. This is the longitudinal force acting on the pressure bulkheads at the nose and tail, trying to stretch the entire airplane lengthwise like a rubber band. Now we are back to our biaxial tension model from earlier.
But I'm guessing this isn't equal biaxial tension like our sphere. The forces aren't balanced.
They are drastically unbalanced. Due to the basic physics of a pressurized cylinder, the hoop stress, the bursting force, is always exactly twice the magnitude of the axial stretching force.
Twice as much.
So, using our superposition notation, we have a biaxial state where sigma 2, the axial stress, equals sigma 1, the hook stress, divided by exactly 2.
The vertical pull stretching the plane is only half as strong as the horizontal pull trying to burst it.
Precisely. Now, if you are a naive designer and you punch a perfectly circular window into this unbalanced stress field, the physics fight you. The uneven forces create uneven bunching around the circle.
What's the number?
If you run the mathematics, the maximum localized stress concentration for that circular window hits roughly 2.5 times the nominal stress.
2.5 times. That is a massive multiplier. And the only way an aerospace engineer can survive a multiplier that high is to thicken the entire fuselage. Add more aluminum. Add more weight, which is the mortal enemy of aircraft design.
It is incredibly inefficient. A circular window is carrying a multiplier that is 1.666 times higher than it theoretically needs to be. But this is where Inglis's mathematical lever comes in.
How do we fix it?
We want the stress to be perfectly uniform all the way around the edge of the window. We want to eliminate the hot spots. To achieve that balance in a stress field where the horizontal force is twice the vertical force, we must design a shape that perfectly mirrors that imbalance.
So if the horizontal stress is twice as bad, we make the vertical height of the window twice as tall to give the horizontal stress a smoother, gentler path to flow around.
That is the exact optimization mechanism. We design an elliptical window where the vertical height A is exactly twice the horizontal width B. The ratio is 2 to 1.
2-1.
When you align that vertical oval with the massive hoop stress, the stretched out geometry perfectly counteracts the unbalanced forces. The tangential stress flowing around the window smooths out entirely. The theoretical KT drops to an incredibly efficient uniform 1.5 all the way around the perimeter.
It's just brilliant. It's geometry weaponized against physics. It's the absolute optimum shape, and that is why you look out of a vertical oval when you fly.
It's a beautiful solution.
But let me throw a wrench in the works. Manufacturing perfect mathematical ellipses is, well, it's annoying.
Machinists aren't always fans.
What if a machinist wants to use a shape that's easier to cut? Say, a slot with straight sides and semicircular ends, which I believe is termed an ovaloid, or a square opening with heavily rounded corners. How do those non-elliptical shapes behave?
This brings us to a highly practical concept in stress analysis called the equivalent ellipse. You can accurately predict the stress concentration of a complex rounded geometry by mathematically matching it to an imaginary perfect ellipse that tightly envelops its outer dimensions.
Wait, really? You're saying a square with rounded corners behaves identically to a smooth ellipse?
To the flowing stress field, yes, they are largely indistinguishable. Consider the physical corners, the cusps of that rounded square that protrude slightly outside the boundary of our imaginary enveloping ellipse.
The extra bits of metal.
When researchers conduct photoelastic tests on these complex shapes where they machine the shape out of special translucent plastic and pass polarized light through it while under load, we can physically see the stress fringes light up in vibrant
Like a
colors.
heat map.
Exactly. And we see something remarkable at those protruding corners. They become photoelastically dead,
Dead, meaning the plastic isn't lighting up.
meaning they carry almost zero stress. The stress flow lines rushing around the massive obstacle take the smoothest, most direct path of least resistance.
Oh, I see.
They naturally trace an elliptical path, completely bypassing the physical corners of the square. The material sitting in those corners is essentially structurally useless. It is bypassed by the load, leaving it as a low-stress, dead region.
Wow.
Therefore, the peak stress concentration of the rounded square is practically identical to the theoretical ellipse that encompasses it.
That is wild. The stress flow literally ignores the material that isn't aerodynamic. It carves its own efficient path.
Nature is lazy. It takes the easiest path.
Okay, but a commercial airplane isn't just a tube with a few windows. It is held together by tens of thousands of rivets. We need to transition from single isolated holes to massive patterns. What happens when holes start getting close to each other? Do their individual stress shock waves collide?
They absolutely collide, and they can either destroy each other or save each other. Orientation is the deciding factor. Let's start with the simplest multiple hole scenario. Two identical circular holes drilled into a single flat plate.
Okay, two holes side by side, maybe an inch apart.
Right. Now, how are we applying the load? If you grip the top and bottom of the plate, pulling perpendicular to the imaginary line that connects the two holes.
So the holes are sitting left and right, and I'm pulling north and south.
Exactly. In this perpendicular scenario, the narrow strip of solid metal residing directly between the two holes is trapped. It has to carry a massive, unproportional share of the load because the stress lines from both holes are being shoved into the same central bottleneck.
Double the bunching.
The local stress shoots up significantly compared to the baseline of a single isolated hole. You have created a severe weak link.
That makes total intuitive sense. You bottleneck the flow.
But now let's rotate the load. Take that exact same plate with the holes left and right and pull it parallel to the line connecting them. You pull the plate east and west.
Okay, pulling in line with the holes.
An utterly counterintuitive physical phenomenon occurs. The two holes actually shield each other.
Shield each other, like race cars drafting behind each other on a straightaway to cut wind resistance.
That is an exceptionally accurate analogy. The first hole encounters the primary stress flow lines, parting them, forcing them to detour out and around its perimeter.
Right, pushing the flow wide.
But before those parted stress lines have the physical distance to smoothly close back in and return to their uniform flat plate state, they immediately crash into the second hole.
So the strip of metal sitting directly between the two holes is literally sitting in the aerodynamic wake of the first hole.
Yes. It becomes another low-stress dead zone. Because of this drafting effect, the maximum stress concentration on the extreme outside edges of those holes actually drops below the multiplier of 3 that we see for a single lonely hole.
It goes down.
The closer the holes get to each other in this parallel orientation, the deeper the wake and the better they shield each other.
That completely upends how you think about removing material. You're telling me that drilling a second hole right next to my first hole can actually lower the peak stress on my part.
Welcome to the beautiful, counterintuitive world of interactive stress fields. Sometimes adding a void relieves a bottleneck.
Which naturally brings me to industrial applications. If two holes interact, what about 2000? I'm thinking of massive infrastructure components, shell and tube heat exchangers in refineries, or the colossal core support plates sitting inside nuclear reactors.
Massive grids of holes.
These thick slabs of steel are perforated with incredibly dense grids of holes.
Oh.
How does an engineer even begin to map the stress when the entire part is more hole than metal?
When dealing with densely perforated plates, calculating individual interaction effects is impossible. We zoom out and define a macro-level engineering metric called ligament efficiency.
Ligament efficiency. Break down the mechanics of that ratio.
The ligament is simply the thin bridge of solid material remaining between any two adjacent holes.
The metal between them.
The efficiency is a simple mathematical ratio. The minimum physical distance of that solid ligament divided by the total pitch, the distance between the exact center points of those same two holes.
So if the holes are massive and nearly touching, the solid ligament is microscopic, and your efficiency drops towards 0%. If the holes are tiny and spaced 10 feet apart, the ligament is huge and the efficiency approaches 100%.
Exactly. And the massive manuals of stress concentration factors for these reactor plates are all plotted linearly against this ligament efficiency. But the absolute most critical factor isn't just the spacing, it's the geometry of the grid.
The pattern.
Whether the designer chooses to arrange the holes in a square grid, a triangular grid, or a diamond pattern entirely changes how the physical load navigates the maze of ligaments.
Is there a clear winner? Does one pattern just flow better?
It is entirely dependent on the primary load vector, but generally speaking, for states of equal biaxial tension, which is exactly what you find in pressurized reactor plates, triangular hole patterns are vastly superior to square patterns.
Why? Because a square grid creates straight, continuous lines of weakness.
Partly, yes.
Yeah.
A square grid creates severe bottlenecks where the perpendicular ligaments intersect, but a triangular staggered pattern optimizes the stress flow because it provides the load with continuous, diagonal, uninterrupted pathways to travel down.
Wow. Diagonal paths.
The stress can weave through the staggered ligaments much more gently, avoiding the harsh right-angle bottlenecks of a square grid.
Wait, you mentioned nuclear reactor plates. Those aren't just holding a static weight. They are heating up, cooling down, pressurizing, and vibrating continuously for 40 years. The load is cyclic. When a part full of interacting holes is subjected to constant cyclic loading, how do these stress multipliers translate to fatigue life?
This raises an important question, and you have just touched on perhaps the single most critical warning I can issue in this entire deep dive. Cyclic loading introduces the terrifying reality of fatigue failure.
Fatigue is a killer.
When an engineer is estimating the fatigue strength for a perforated part, they must calculate a reduced fatigue limit by applying a material property called the notch sensitivity factor, denoted by the letter Q.
Okay, Q tells us how sensitive the specific metal is to having a hole in it under vibration.
Correct. But here's the fatal trap. When applying Q to your equations, you must apply it specifically to the net stress concentration factor, KTN. You absolutely unequivocally cannot apply it to the gross factor, KTG.
Let me push back on that to understand the severity. What is the actual consequence if a tired engineer at 2 a.m. accidentally plugs KTG into their fatigue software instead of KTN? Is it just a slightly less conservative safety margin?
No, it is much worse than that. Let's run a thought experiment. Imagine you are designing a steel I-beam for a bridge, and you drill a massive row of holes down the center of the web to lighten it.
Okay, so it's cheese bee.
The baseline steel has a fatigue limit of, say, 30,000 psi before it cracks. If you mistakenly use the gross factor, KTG, to calculate your new fatigue limit, your mathematics will produce an absurd, physically impossible result.
How absurd.
The math will erroneously tell you that your Swiss cheese beam actually has a higher fatigue limit than a solid, uncut piece of steel. It will tell you the holes made the metal immune to vibration.
Wait, the math will output a number higher than 30,000 psi. It will literally lie to you and say removing metal made it physically stronger under cyclic load.
Yes. And the reason for the lie is double counting. The gross factor, KTG, already mathematically bakes in the effect of the lost cross-sectional area. It averages the stress over the whole imaginary uncut plate.
Right, the fantasy math.
By applying the notch sensitivity Q to KTG, you are effectively double counting the missing material. This mathematical error artificially inflates the perceived strength of the remaining ligaments.
That's a huge blind spot.
Your software will output a net fatigue limit of, say, 38,000 psi. You will certify the bridge for highway traffic, believing you have a massive safety margin. But the true net fatigue limit at the localized bottlenecks might only be 15,000 psi.
Half as strong as you thought.
The bridge will endure a fraction of its design life. Cyclic fatigue cracks will rapidly initiate at the net ligaments, and the structure will catastrophically fail.
That is a chilling mathematical illusion. You think you have a 20% safety buffer, but you actually have a 50% deficit. Design junkies, tattoo that on your forearms. Always use KTN for fatigue calculations in patterned elements. Now, I want to pivot. Because everything we have discussed so far, from the infinite plates to the de Havilland Comet windows to the reactor grids, assumes we're dealing with relatively thin sheets of metal, two-dimensional problems.
Right, plain stress.
But my background is in heavy machinery. I deal with massive, thick, cubic blocks of hydraulic steel. And my skeptical brain is asking, does the stress multiplier behave differently when it has to travel down the deep, dark barrel of a 3-inch long hole.
Your skeptical brain is touching on the frontier of three-dimensional elasticity.
Hmm.
For decades, engineers assumed that the 2D plane stress solutions we just discussed applied uniformly all the way down the bore of a thick part.
That would be the easy assumption.
But researchers Eli Sternberg and M.A. Sadowski conducted rigorous 3D elastic analyses that shattered those two-dimensional assumptions. They delivered a revelation about thick plates that completely upended forensic failure analysis.
Lay the 3D reality on us.
In a thick element subjected to tension, the maximum stress is not uniform down the barrel of the transverse hole. It varies wildly.
Okay, so it changes. My intuition says the stress must be highest right at the top and bottom exterior surfaces of the block, where the metal meets the air. That's where the material is least supported.
That is the universal intuitive guess, and it is completely wrong.
Really?
Sternberg and Sadowski proved that the stress is actually slightly lower at the exterior surfaces. It reaches its absolute peak multiplier slightly inside the interior of the hole.
Below the surface.
As you move from the visible surface down into the dark bore, the stress climbs to a maximum localized peak before finally settling into a uniform distribution deeper inside.
That defies common sense. Why would the metal trapped deep inside the hole experience worse stress than the exposed metal on the surface?
It comes down to the Poisson effect and material constraint. When you stretch a block of metal longitudinally, it naturally wants to contract or neck down laterally.
Like stretching a rubber band.
The metal right at the exterior surface is free to contract. It has nothing but empty air pushing back against it. That physical deformation relieves some of the localized stress.
But the metal buried half an inch down inside the bore.
Exactly. The interior metal is completely surrounded and trapped by the bulk mass of the surrounding steel. It wants to contract laterally due to the Poisson effect, but the surrounding metal fiercely resists it.
It's locked in place.
This constraint creates a complex state of triaxial tension. The material is being pulled in three directions at once, preventing it from yielding or deforming to relieve the primary load. This triaxial constraint drives the von Mises equivalent stress to its absolute maximum, slightly below the surface.
Think about how utterly terrifying that is for a maintenance technician. If a hydraulic block is nearing the end of its fatigue life, a tech might shine a flashlight on the exterior surface of the hole, see absolutely zero cracking, and sign off the part is safe.
It's a false sense of security.
Meanwhile, due to that triaxial constraint, a microscopic fatigue crack has already initiated invisibly down inside the barrel of the bore, propagating outward where no one can see it until the block violently splits in half.
It happens constantly in heavy industry. It is a prime example of why three-dimensional elasticity cannot be ignored. The standard 2D KT factors from the textbooks are usually mathematically conservative enough to ensure your basic design survives.
But for forensics,
For forensic failure analysis, when you are trying to find where the murder weapon is hidden, you must understand that the crack almost certainly initiated deep inside the hole, not on the convenient visible surface.
okay, what about holes that intentionally alter the surface? I'm thinking of countersunk holes. Earlier, we talked about aerospace skins needing to be aerodynamically perfectly smooth.
Yes, countersunk rivets.
So they machine a conical divot into the top of the hole so the rivet head sits flush. Where is the stress peaking in a complex 3D shape like that?
Extensive finite element simulations reveal a very distinct failure point for countersunk holes under tension. The maximum stress does not occur on the smooth slope of the cone, nor does it occur deep in the straight bore. It occurs exactly at the sharp root.
The root being that specific transition line where the angled cone of the countersink terminates and meets the straight vertical shank of the main bore.
Correct. It is a harsh, sudden change in internal geometry, and the stress flow lines bunch up violently exactly at that transition line, specifically at the flanks 90 degrees away from the direction of the pull.
Right, the east and west flanks.
And the data reveals a highly counterintuitive detail. Changing the angle of that countersink cone does practically nothing to help you. Varying it from a steep 90-degree cone to a shallow 100-degree cone barely nudges the stress concentration multiplier.
So if I have a failing design, I can't just tell the machinist to tweak the angle to make it gentler. What actually controls the failure risk?
Depth. The failure risk is strictly driven by the depth of the countersink relative to the total thickness of the plate.
How much metal you leave behind.
If you carve away too much of the plate's structural thickness to sink the rivet head, leaving only a thin sliver of straight shank, the stress at that sharp root multiplies exponentially. You are effectively severing the load path.
Which brings us to perhaps the most horrifying 3D stress scenario imaginable. The absolute nightmare of fluid dynamics engineers. Crossbores. Let's visualize what a crossbore actually is for the audience.
Picture a massive solid block of forged steel forming the high-pressure head of an industrial compressor. You drill a main bore straight down the center to carry fluid at immense pressure,
Okay.
but the fluid needs to go somewhere else. So you drill a secondary intersecting tunnel straight through the thick side wall of the block, crashing directly into the main bore at a perfect dead-on 90-degree angle. That intersection point is a crossbore.
You have two internal cylinders intersecting at a hard right angle, buried inside a block of steel, packed with pressurized fluid trying to burst out. That sounds like a mathematical disaster area.
It is arguably the most severe localized 3D stress concentration you will routinely encounter in mechanical design. The fluid pressure is aggressively trying to pry that sharp 90-degree internal corner wide open.
How bad is the multiplier?
A researcher named W.F. Riley conducted some incredibly precise three-dimensional photoelastic tests on these exact crossbore intersections. He froze the stress states into plastic models and sliced them open. For his specific test geometries, he found that the maximum nominal stress factor hovering right at that sharp internal crotch was around 3.6.
But wait, earlier you said the baseline for a circle was 3, so 3.6 is bad, but it doesn't sound like a total disaster. But that's just the nominal factor for his specific finite test block, right?
Exactly. His block had outer boundaries that interfered with the pure theoretical multiplier. If you take Riley's empirical data and extrapolate it out to estimate the true theoretical infinite body factor,
The unadulterated geometry.
the pure geometric multiplier without the outer walls of the block softening the blow, the estimated theoretical KT sits at an astonishing 4.7.
Nearly 5 times the nominal stress. Localized at a microscopic, sharp, internal corner buried in the dark where you can never inspect it. How does an engineer even fix that? You can't just leave a multiplier of 5 inside a 10,000 psi compressor block.
You can't. If you leave it sharp, it will rapidly fatigue and violently burst. The ultimate engineering fix to survive a crossbore involves a rigorous two-step mitigation strategy. First, whenever physically and hydraulically possible, you must make the two intersecting holes the exact same diameter.
Why does equal size matter?
The finite element mathematics and physical strain gauge measurements decisively prove that unequal diameters, say a small pilot hole crashing into a massive main bore, create much sharper, highly asymmetric stress concentrations at the junction. Equal diameters balance the disruption.
Okay, that's step 1.
The second step is much harder. You must physically reach deep inside that blind intersection and completely round off the sharp internal corner where the two cylinders meet.
You have to machine a smooth radius into an interior corner you can't even see.
Yes. You must use specialized radiusing tools to carve away that sharp 90-degree cliff. By creating a smooth, sweeping transition radius, you physically force the stress lines to take a gentle, sweeping path around the corner instead of crashing into a dead end.
Those are work.
If you execute that internal radius perfectly, the mathematics show you can theoretically drop the localized KT from near 5 all the way down close to 1. But from a manufacturing standpoint, it is notoriously difficult and expensive to machine a perfect, polished radius deep inside a blind intersection.
It's the classic battle between what the physics demand and what the machine shop can actually physically build. Which brings us perfectly to our final problem, the ultimate practical compromise.
Sometimes you just have to drill the hole.
I am an engineer. I am forced by the assembly layout to put a hole right in the middle of a highly stressed panel. I don't have the space or the money to change the shape to a beautiful, optimized English ellipse. I am stuck with a standard circular drilled hole. How do I physically reinforce that circle so my part doesn't snap in half?
If you are trapped with a circle in a high-stress field, you must utilize the art of the reinforcement bead. You intentionally manufacture the part with a thickened, integral ring of solid material completely surrounding the hole, much like the thickened grommet around a shoelace hole.
Just beefing up the perimeter by adding a donut of extra metal.
Conceptually, yes. But mechanically, you completely alter the stress landscape. When you add that thickened reinforcement ring, you solve one problem but create another. You no longer have just one single failure point to worry about. You now have to rigorously analyze two distinct competing locations.
Okay, what is the first location?
The first is the exact inner edge of the hole itself. Just like the baseline flat plate, you add a material so the net stress is lower, but the multiplier effect of the circle is still sitting right there at the boundary.
Makes sense. And the second location?
The second location is the outer perimeter junction, the exact line where your thin, flat panel abruptly steps up and meets the thick wall of the reinforcement ring.
Ah, because that sudden stair-step change in thickness is itself a geometric obstacle. The stress flow lines flowing through the thin panel suddenly smash into a wall of thick metal. That's going to cause its own bunching effect.
Exactly. You are essentially trading one massive, concentrated stress point at the hole for two moderately smaller stress points, one at the hole, one at the step. And because the stress fields at that thickness junction are highly complex and acting in 3 dimensions, we can't just use simple 2D multipliers.
We have to combine them.
We have to evaluate them using the von Mises equivalent stress formula, which takes all the competing principal stresses, pulling in different directions, and combines them into one reliable, digestible failure metric.
Okay, so if adding a thicker ring makes the hole stronger, my engineer brain immediately takes that to the logical extreme. Does making the reinforcement ring wider and wider, stretching it out like a massive frisbee, and making it thicker and thicker, just keep making the part infinitely stronger? Can I just brute force the physics with enough mass?
I smile every time I hear that specific assumption, because the photoelastic data reveals a harsh, undeniable reality, an emphatic no. You cannot brute force the physics. There is a strict mathematical law of diminishing returns when adding mass.
Explain the physics of why more metal stops helping.
Let's say you cast a reinforcement ring that is incredibly wide. The diameter of the bead is 5 times the diameter of the hole. When researchers load that massive ring and view it under polarized light, the photoelastic data clearly shows that the outermost fringes of that incredibly wide ring actually become photoelastically dead.
Just like the corners of the rounded square. They carry absolutely zero stress.
Exactly the same mechanism. The stress flow lines moving at the speed of sound through the steel simply do not have the physical time or geometric inclination to migrate all the way out to the extreme outer edges of your massive ring before the hole is already behind them.
They just take the shortcut.
They take the shorter, tighter path near the center. So you have bolted on all this massive, heavy material, and the physics are actively ignoring it. It is doing absolutely nothing to carry the load. It is just parasitic dead weight.
And in aerospace or automotive design, parasitic dead weight is the ultimate enemy. It burns fuel and ruins payload. So if a massive frisbee is useless, what is the optimum ratio? How do I tune this geometry to get the absolute maximum strength for the absolute minimum added weight?
Through decades of testing, the mathematical sweet spot has been clearly identified. To achieve optimum efficiency, the ideal total thickness of your reinforcement ring should be roughly 2 to 3 times the baseline thickness of your panel.
Let me visualize that. If my primary aluminum skin panel is 1 inch thick, my reinforcement ring should protrude so the total thickness at the hole is between 2 and 3 inches.
Yes. That specific 2 to 3 ratio provides enough mass to significantly blunt the stress bunching without entering the zone of dead weight. The performance curves demonstrate that the absolute largest, most dramatic gains in reducing your KT happen with relatively tiny initial additions of volume.
Small changes, big results.
If you add just a little bit of smart mass, you can drop a terrifying KT of 3.0 down to a highly manageable 1.5 very efficiently.
But what if I am an absolute perfectionist? What if I want a KT of perfectly 1.0? I want to add enough metal so the hole becomes completely invisible to the stress field, as if it was never drilled at all.
The curves of the graph asymptote violently. Trying to force your KT perfectly back down to 1.0 is a fool's errand. It requires a massive, heavy, and highly inefficient volume of material.
You'd have to make the ring enormous.
To fight for that last 10% of stress reduction, you have to add an exponential amount of mass. For aerospace engineers, that is almost always a catastrophic trade-off. A smart designer readily accepts a KT of 1.2 or 1.3, mitigating the peak danger in order to save hundreds of pounds of payload over the entire aircraft. You compromise with the physics, you don't try to defeat them entirely.
Wow. Okay, we need to land the plane on this masterclass. We have been on an incredible journey today. We started with the violent reality of a microscopic pinhole tripling the stress in a steel continent. We explored how pulling in all directions at once can actually save a pressure vessel, reducing the factor to 2.
It's been a ride.
We dug into the tragic history of square airplane windows and the mathematical elegance of the 2-to-1 vertical ellipse that solved it. We ventured into the terrifying invisible 3D stresses lurking inside crossbores, and we finally established the exact volumetric limits of how much metal you should add to reinforce a simple circle.
It is a dense, mathematically heavy topic, but if you step back, it all comes back to a single philosophy: respecting how force desires to flow through physical geometry. We don't dictate the load path, we merely provide the roads. But I want to leave you and the listeners with a final paradigm shift to ponder as you look at the world.
I am always ready for a paradigm shift.
We spend virtually all of our time in mechanical engineering trying to mitigate, reinforce, and apologize for the damage a hole does to our pristine stress fields. We view voids as the enemy, but I challenge you to look at nature. Look at the cross-section of a human femur bone, the grain structure of oak wood, the microscopic scaffolding of bamboo.
Right.
They are not solid bars of material. They are fundamentally entirely constructed out of microscopic holes.
There are massive cellular structures, entirely made of voids.
Yes. And nature does not view those empty spaces as flaws. Nature uses them deliberately. It doesn't just use them to save weight. It intentionally places specific shapes of holes to arrest propagating microcracks and to softly, actively route catastrophic stress waves around the vital, delicate areas of the organism.
Wow.
The empty space is doing the heavy lifting. The next great frontier of mechanical engineering isn't just learning how to bolt on enough metal to survive the holes we drill. The frontier is learning how to place voids intentionally, creating smart geometries where the nothingness actively, mathematically, guides the force exactly where we want it to go.
That is a profoundly beautiful way to look at it. The void isn't the absence of design. It is the ultimate tool of design. Designing the empty space to be just as functional, just as vital as the solid material surrounding it. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.